Good morning. Uh, this week we'll continue to talk about machine learning and the scikit-learn. So first, I will start with support vector machine. So what you see on the screen is a diagram for illustrate how support vector machine works. Specifically, we are talking about the linear SVM. So it is kind of like the linear regression and the logistic regression. It uses a linear function to separate the two class to do the classification. So you can see that suppose we have two different classes. One is the first one is a black class of the black dots, and the second class we have these white circles. We have two different class of samples. Our goal is to use a straight line, to separate these two different classes. We'll talk about using a nonlinear way to separate different classes, and we can do this even for multi-classes. But right now we are focusing on the linear support vector machine. So our goal is to use a straight line to find out a straight line that separates two different classes of samples. Okay, so how do we find a line to do so, and so that this straight line is the best straight line that separates these two different classes? The criteria that how to determine the best straight line that separates these two different classes is that we're trying to find a straight line so that, okay, so first we find the correct sample in the black class that is closest to this straight line, and the nearest sample, white sample, to this straight line. So we can measure the distance of this nearest sample to the separations. We wish to find a straight line so that the distance can be the minima of these two distance is maximized. So that not only we find a straight line that separates these two classes, but also the nearest sample in black, if we're counting the black samples or white sample, the nearest sample to this straight line is as far as possible. Then that is the best straight line we wish to find. Okay, so not only we want to find a straight line that separates the black samples and the white samples, we wish the margin to be as large as possible. So that's kind of intuitive. We can translate these intuitions into mathematical formula. So basically, we are trying to find a straight line, a function of straight line, wx equals to b. I mean, wx minus b equals to 0. Wx minus b equals to 0. This is our straight line. And we wish that all of the black points, black samples, are on the left side of wx minus b equals to 1. So which means if we put this plug this x into this formula, this equation, wx equals minus b. The value should be greater or equal to 1. In this case, our feature has 2 dimensions, kind of like the logistic regression and linear regression. The situation is the same. And we feed all the features into this linear formula, and we get a value, wx minus b. Our goal is to make all of these black samples, if we plug into this equation, the value should be greater or equal to 1. And for all the white samples, the value should be less or equal to -1. And in fact, the distance, if we compute the distance, you can find the distance of this the length of this margin is the length of W. 2 over the length of W, which means if we want to minimize, the distance, then we are going to maximize the norm of W. So that's the idea of the linear subperfect machine. We simply try to find a linear equation that satisfies this condition, both of these conditions, and try to minimize this 2 over the norm of W. If we really do so, we can actually visualize as what we did for logistic regression and linear regression. So again, we have two classes of samples. The first one is the positive numbers. The second one is the negative numbers. Recall that the red line is what if we do the linear regression on these samples. This is what we do for linear regressions, and this is the decision boundary. Kind of biased or shift against to the ground truth. One way to fix that is to use logistic regression. So we modify the shape of this straight line into the sigmoid function, which is more like a step function, to avoid these issues. But the linear subperfect machine, although it is also using linear function to do the classification, it takes a different approach. By using this approach, it doesn't consider the shape of the functions. It simply using the to design the. It's still using. You can see that the green line is still a straight line, kind of like the red line. It doesn't modify the shape of the function, but instead it uses a different way to measure the loss. It only considers the first element. I mean the nearest element. It only considers the nearest element. So recall that the issue of using a straight line directly like linear regression is that even though if we are using we have a perfect decision boundary and everything is the perfect thing for this red line, we still got a lot of loss, because I mean, if you see that the red line is going to approach to infinite, so the loss is going to be great, because all the samples has a y value to be either 1 or -1. So the loss is going to be great. However, by solving these issues, the support vector machine consider only the nearest samples, the closest samples, and forcing the value of closest samples to be 1 and -1. So it will pass through the nearest sample. The line is the linear line. There's still a linear line equation here. The linear line equation passes through the nearest sample, the nearest negative sample, and the nearest positive sample. And it only considers it considers loss in a different way. So it will have the same issue as linear regression, although it still determines a linear line. It doesn't, you can see that this green line is even accelerated faster than the red line, but it doesn't share the same issue because the differences between for example, this maybe this is far below and this is far up, and they are not coincident with all these blue samples and this blue sample. However, they didn't contribute to the loss because we are computing the loss in a different way, a totally different way. We only consider the tangent, the slope of these things, and as a result, the decision boundary is quite easy to determine. In this case, for support vector machine, the decision boundary is exactly in the middle of the the nearest negative sample and the nearest positive sample. Or in another way to state this, the decision boundary is exactly the average of the mean of the smallest positive sample and the largest negative sample. Because we are talking about the nearest samples in negative class, or nearest sample in the positive class, so we need to give a name of this nearest sample, or this, like this one, this black one, or and this white one, or in this case, this one and this one. This sample are called the support vector. Also, that's what the name support vector machine comes from. This sample, we call this sample the support vector. So in this terminology, our decision boundary is exactly in the middle of these two support vectors. So that's our decision boundary. Or in mathematical formula, we can write this formally. We have two constraints, or we have two constraints. That is, okay, in the first class, wxi for each x, wxi minus b should be greater or equal to 1. And for the second class, wxi minus b should be equal to or less to -1. So this is our two constraints. However, by a simple trick, we can combine these two classes into one simple class. Recall that we haven't used the y or the ci yet. So we are using y. We call it, in this case, we call the y as our ci. Yi as our ci, because c stands for the class, for different class, the first class or second class. Because we are only considering the binary classification. So this ci means the class. pretty much exactly the same as this what we are doing right here. For all positive, which is the first class, for all positive class, we give it a value 1. And for all negative class, all samples in the negative class, we associate it with a value -1. So this 1 and -1 is CI in this formula. It's the CI in this formula. So we can simplify these two constraints into just one, because for the positive class, for the first class, because CI is exactly 1. So this formula is the same as this formula, the first formula, the first inequality. And for the second class, because CI is -1, then this inequality is equivalent to the second one. So by using this simple trick to use CI to be either 1 for the first class or the -1 for the second class, we can combine these two constraints, two inequality, into just simple one inequality. But basically, they are exactly the same. It's just that we can write it more concisely, more in a more compact way. So just in one line. That's all. Fundamentally, they are exactly the same. Okay. Okay, so I think I said something wrong before. We wish to maximize the distance. So we want to maximize the distance. So we want to minimize the norm of W. I say that in the opposite way. I kind of get a little bit confused. It's still in the morning. I was kind of confused. But let me say it again. We want to maximize the margin. We want to maximize the margin. That is, we want to maximize the value of 2 over the norm of W. We want to maximize this value. Equivalently, we want to minimize the norm of W. That's the correct statement. So here you can see that we are trying to minimize the norm of W, subject to this constraint, or these two constraints, in fact, but we can write it in a simple line, in one line. Okay, so that's the whole optimization problem we wish to solve if in order to optimize our support vector machine. So the weight is W, and maybe you have a B right here, but the B, you don't need to optimize the B, you just want to find the B that you can satisfy this condition. We only want to minimize this guy, but all of the W and the B are parameters that you can adjust. Okay, so let's move to the next more issues about this approach. One apparent issue is that what if we cannot find a straight line that separates these two classes? This class is what this situation is what we call linear inseparable. If we can find a straight line that separates these two different classes, then we call this case linear separable. So by using this terminology, our issue is what if what if our samples, our training data is not linear separable? If this is not linear separable, then we cannot even find any straight line that satisfy the constraints. Let alone to minimize these guys, because there's no W and B we can find to satisfy this constraint. And this happens very often, very frequently, because you can see that this is the iris dataset we were talking about we were mentioned in discussed in last lecture, and this is one of the simple training data. So what happens if they are not separable? So one way to do that is to solve this as a way that we call the soft margin. The soft margin. We still minimize these things and subject to some constraint. But instead of strictly ask it to be greater or equal to 1, we allow it to have some miss or some say some margin. This is called soft margin. There's some error. So in some, it allows you to have some penalty. We consider this as penalty. So if some xi does not satisfy this the formula, the inequality strictly, that's okay. We just introduce some penalties right here, the eta I here, some penalty. And of course, this penalty need to be integrated to our optimization problem. So if the condition does not satisfy strictly, if it is satisfied, we can choose this to be 0, because it cannot be negative 0. If you are, consider this case. If you are on this side, then it is exactly the same as the original unmodified support vector machine. We still get the benefit of support vector machine. But if in some case that we cannot fully fulfill the requirement of the original, the strict requirement, the strict constraints of the support vector machine, that's okay. But you have to pay some penalty right here. So instead to minimize the norm of W directly, we minimize this norm plus if there are some samples does not follow the requirement, the constraint strictly, that's okay. You just need to pay some penalty. So we minimize the norm as along with the penalties. Of course, there has to be a constant to decide how much the penalty is comparing to the original optimization target, the norm. So we introduce a C, constant C here, so that we can adjust the scale of the penalty. So this is called a soft margin. One of the benefits of this soft margin things is that it plays very well with the dual optimization problem of the support vector machine. So of course, this is a very usual technique when we wish to make things that is more robust. If it is not linear separable, okay, that's okay. We introduce some penalties so that for the case that does not fulfill the strict constraints, we just give some penalties. But there are many different ways to give some penalties. This particular way is one of the good ones that it plays very well mathematically, because the dual form can be write, a dual problem can be write very clean and easily, so that we can ignore all these penalties to have pretty much the same dual problem formulation. So what is the dual problem formulation? I won't go too deep details into the mathematic technique, but in general, if we are given optimization problem, that is to find the minima uh, or finding the maxima subjects to some constraints. That's a typical statement of a optimization problem. Let's say just when we try to find a minima subject to some constraints, usually there are way to transform this problem into another form. That is, in a lot of cases, they are equivalent, or at least in other cases, give some upper bound or lower bound to your solution. In a lot of good problems, you can find an equivalent statement to transform a minimized optimization problem into a maximized optimization problem. So in our case, originally we have a minimized problem, and now the dual problem is to maximize something. And not only we transform the minimized problem into a maximized problem, the thing is the variable and the constraints change their roles. So each of recall that the variables here are W, and our subjects to these constraints for each samples, x1, x2, x3, we have a lot of black samples and a lot of white sample, or a lot of samples in the first class and a lot of samples in the second class. Say our training data has 1,000 samples, then we have 1,000 constraints. So in the dual problem, the role of variables and the constraints changes role. So in this case, in this dual problem, we will have 1,000 variables instead of just the dimension of the W, the dimension of the features. Okay, let me make a more concrete example here, because we can actually count the things. So in this case specifically, this is a two-dimensional feature. So W has two dimensions. The dimension of W is 2. And we probably have 1B. So we are optimizing a 3-variable problem over, there are two variables for W and 1 variable for B. 1 variable for B. So we're optimizing over these 3 variables. But we have how many constraints do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 8 samples in the first class and 8 samples in the second class. So we have 16 constraints total. So here we are pretty much optimize over this W3 samples. In at least in the original one, we are optimized over W and B, but we have like 16 constraints. For a soft margin, we introduce the penalties. So we are going to have more variables, like 3 plus 16. But here, because we swap the roles of constraints and variables. So the dual problem of the SVM optimization problem, we will have 16 variables here, each one corresponding to the constraint, each of the constraint. And each of the variable here is going to become a constraint right here. So we switch the role of constraints and the variables. Okay, let's see what the dual problem is. The dual problem is basically still a quadratic things, but instead of optimizing through the W, we're optimizing this CI, C1 to Cn. We optimize this CI, and each CI should be in this range, and subject to all of this is going to be 0. And in fact, if everything has have good properties, the dual problem should be go back to the original one, so that they are all equivalent in some way. In this case, they are in fact the good ones. So we can, if we solve the dual problem, we can find the W of the original problem, the original optimization problem, by using this formula. So Ci, Yi, Xi, we sum this up and we find the W. So they are basically the same problem. It just, in some case, solving a dual problem is easier, and solving the original one is much more complicated. So in that case, we are going to solve the dual problem. The original one is called the primal optimization problem, and the dual problem is called the dual problem. So sometimes we solve the primal problem directly, and sometimes we solve the dual problem. So by using these mathematical properties, we have a choice. And sometimes the dual problem and the original problem are, both of them are hard to solve. Then that's fine, because at least we get a chance to transform this problem into a different one, and a different one, at least we got some chance that the dual problem is easier to solve. So that's the idea. And in the case of supervised machine, a lot of algorithms are in fact solving this guy into a dual problem. And also, the dual problem allow us to introduce a method called the kernel trick, or kernel method, that we are going to discuss a little while later, a little moment later. But right now, let's deal with another issue, that is the nonlinearity. And in fact, the kernel method and the kernel trick is a way to deal with nonlinearity. So this is by using the supervised machine apply on the iris dataset. If we are using two of the feature and applying it to, because in iris dataset we have 3 different classes, we're picking 2 of them, and it has 4 features. We pick 2 of the 4 two features out of the 4 features. So you can see one thing is it is not strict, it is soft. We use soft margin. And another thing you can observe that is it has a nonlinear boundary. It still has a margin. You can see the dot, the dashed line here. The dashed line here indicate the different margin. And the solid curve, solid black curve right here is the decision boundary. So it is still has the same concept of the linear support vector machine. It's just that we have a nonlinear boundary and nonlinear thing. We have encountered similar things in the linear regression and the logistic regression. Recall that in the linear regression, we introduced a randomized feature. Just generate random features from the original one, and it can improve the accuracy for classifying the MNIST dataset from like 85 to 96 or 97. Or I think it beat the nearest neighbor method, so it can achieve at least 98% accuracy. So that's one way to do that, to introduce random features. And we also introduce the polynomial features when we talk about the logistic regression. And in fact, you can apply the polynomial features on the linear regression as well, so that becomes a polynomial regression. So in this case, it is the same. We can do the similar thing by using polynomial features or by using other way to generate features. However, because of the good property of the dual problem, there is a easier way to do so, or more elegant way to do so. That's called the kernel trick. But before we're talking about the detail of kernel trick, let's first say I want to convince you that by introducing new features, we will transform something that is linear non-separable into something that is linear separable. So this is a toy example for illustrating these issues. The way how you can find this in our notebook, in our class repo notebook. So let me put it right here. Okay. So this is a notebook, the 05 notebooks right here. The way that the sample generated is quite easy. All of the purple things are in a circle. You can say that either it is greater than 1 or not greater than 1. So it is in fact in a unit circle, and all the red dots are outside the unit circle. That's it. So it's a quite simple thing. If you are considering the radius, or if you consider a polar coordinate, but since we are considering Cartesian coordinates, it is definitely not linear separable. So you can see that when we apply the support vector machine, you'll get a decision boundary, something like this one, which is not very I mean, I'm using support vector machine algorithm to find a good decision boundary, a good straight line that separated. But in fact, the thing is, the fact is that no straight line can separate these two classes, so that the line founded by support vector machine is not very good. It's no better than a random straight line that you just draw some straight line randomly, because they are equally poor. But I mean, you can easily see that it is impossible to find a straight line that separates the points in a unit circle and the points outside the unit circle. Instead, what we can do is we can introduce some more features, like the polynomial features. especially polynomial feature, because we know that the circle can be defined in a quadratic polynomial. That is, if we have something called x squared plus y squared, or x1 squared plus x2 squared, if we can have this value, it's pretty easy to classify these two classes, to separate this class, because if x1 squared plus x2 squared is greater than 1, then it should be in the red class. If x1 squared plus x2 squared is less than 1, it should in purple class. That's easy. That is very easy. Almost as easy as the toy example we are talking about, the positive number and the negative number. We only need one feature, that is x1 squared plus x2 squared. So we know that it should be work very well if we introduce the polynomial features. So in fact, it is, and we can visualize in 3 dimensions. We can visualize it in 3 dimensions. This is the level curve. This is the level curve of the support vector machine. Because we introduced the new features, the polynomial features. So this one looks not like, it is not like a linear or like a plane. It looks more curved. This is similar to the case what we do for like a logistic regression, because originally for linear regression, it become a straight line. But since we introduce new features, this becomes a quadratic surface. This becomes a quadratic surface. So by using this quadratic surface, we can easily separate the purple samples and the red samples. One remark is this example is analogy to the toy example here. Instead, it's just that we have 2 features. In these examples, we have only 1 features. But in this graph, we have two features, and the height should be considered z-axis, serve as the same purpose of the y-axis in the positive negative toy example. So they serve the similar things. They have some so in fact, the decision boundary is the circle itself. It becomes the circle itself. It is this surface, the section of this surface to the plane z equals to 0. It will becomes a circle, because we are using the quadratic polynomial features. So that's similar, pretty much the same when we do for what we do for the logistic regression or linear regression. And you can also use the randomized features or all other different features. However, how do we choose the feature? In the previous example, we know exactly what we wish to find because we know the quadratic polynomial works. But in general, how do you know what features you want to pick? A practical way is we find the experts of this problem and handcraft certain features, or we have a educated guess to construct features that we think is relevant and useful. That's one way to do that, but that is always a big work. Another way is, of course, we use the randomized. We can use the randomized way to generate features, and we already see how powerful the randomized feature is. So can we do the similar things? Yes, we can do that. But if we have more features, the things is going to be more complicated. And the optimization problem becomes more difficult to do that. So we are we want to find simpler or more elegant way to solve the issue. At least if we have different ways to deal with the same problem, we can at least choose one of the best way to do so. So kernel trick is one of the alternative way. They can find an equivalent solution, but the idea is that instead of finding the feature directly, we are kind of mapping it into a infinite dimension space. Not only just like recall that when we use the polynomial features, apply polynomial features on the MNIST dataset, because originally the MNIST dataset, each sample had 784 features. So after applying the quadratic polynomial features transformation, we get like 50,000 or like 500,000 parameters. So that's a lot of different parameters, a lot of different features we want to have. But by using kernel trick, we can easily to have infinitely many features. Don't worry too much about it because our data set only have finite samples. So in practice, it will only live in a finite dimension inside an infinite dimension space, because you only have finite many samples. So for example, if we have only 2 samples in our data set and we have a 3-dimensional world, if you have 2 samples, these 2 samples will lie in a straight line. So although we are in a 3-dimensional space, but suppose your dataset only have 2 samples. These 2 samples are practically live in a 1-dimensional subspace in this 3-dimensional space. Similar, if we have only 3 samples, these 3 samples will lie into a plane. So they are effectively live in a 2-dimensional space inside our 3-dimensional space. This is simple. Ideally, conceptually, we are sort of mapping these samples into a infinitely dimensional space. But I mean, don't worry too much about the computation cost, because they are practically effectively they are living in still in a finite dimension. But this treatment we can unify and don't need to worry about the feature selection. So just suppose we are transform our data by using this transformation. This transformation is just conceptual. Suppose we are mapping these things into an infinite dimension space. We'll get rid of this because we don't need the whole point of kernel tricks is that we don't need this function anymore. But we can have all the benefit of this function, this mapping. So suppose we have a mapping from our feature space into an infinite dimension feature space. There are different choice of this function, not directly, but by defining this k. Okay, so the whole point of kernel tricks is that we only need to define the k. What is the k? The kernel k. The function k is the inner product of these 2 samples, but not directly in our original space. The inner product of these 2 samples in the infinite dimensional space in the mapped space in the new space. Okay, so the all information we need to solve the optimization problem of support favorite machine is this information, the k, x, I, y, j. That is the inner product of these two samples in the target, in the infinite, in the mapped feature, in the new feature space. That is all we need. Their inner product. We only need this information. But we want to derive the mathematical formula, so we still need these symbols here. Okay, but just give you a remark that we'll get rid of this mapping. We don't need this mapping directly. We only need this kernel function, the inner product between them. We only need this information. Of course, this function need to satisfy some certain property. For one thing, that the inner product should be greater or equal to 0, and the inner product of the self should be positive. And also other thing, it should be something called the positive benefit. But for a second, we don't need to worry too much about it, because we will provide some common choice of kernel later. Also, this function is called kernel. So let's see how we can ignore all this the phi function here. We can ignore the mapping phi here and use the kernel directly. Okay, we'll still go to the original dual problem here. This is the original dual problem. We want to maximize this guy and to minimize subject to this constraint. The constraint does not involve with, because we are mapping the features only. So the constraint only involved with ci and yi. It doesn't involve with x. So we don't need to worry about the mapping. They are still the same. The only thing is here, the only difference here, the xit, xj. But this one is the inner product, right? So that's why if we try to solve the dual problem, we only need to know the information of the kernel. We don't need to know the mapping. We don't have to use the mapping directly. However, recall that when we there's an issue, that is, recall that when we solve the after we solve the dual problem, we still need to use the solved problem to actually apply to new data, like wx minus b, to check whether it is positive or negative, so we can do the prediction. But as you can see here, if we wish to construct the w back, we still need the xi. So in this case, if we are using the new feature space, we still need the mapping. So how can we do that without using the mapping directly? Surely we can solve the optimization problem to find the C1, C2, Cn that we want. But and by the way, C1, C2, Cn is finite because our dataset is finite. We don't need to worry about the dimension. If you do the primer, then you have to worry about dimension, because suppose you are mapping into the infinite dimension space, then you will have infinite many parameters you need to optimize. But since we are only work with the dual problem, it automatically solved, because the constraints become the variable, and we only have finite constraints. the finite number of constraints, the number is equal to the number of samples. So the issue automatically solved. However, this one seems to be a little need to be worried about. Let's see a detail. So this one is we rewrite the formulas into the form of the new feature space. So we write it specifically, explicitly that the things is mapping into the new feature, and we take the inner product. So this one becomes the k xi y j. Also, we write it down specifically so you can see. Yes, we don't need the feed mappings right here. We only need k right here, and the constraints is not modified. It is exactly the same thing. About the finding the w, instead of finding a w, because we cannot find that w, we don't have the v. If we don't have the v, we cannot find w. That's true, but we can still use the w on the problem to do a prediction, because what we are trying to do is to find the w x minus b, which what we do is find the w x minus b. We are trying to find w x minus b. But what is w x minus b? The w, let's substitute these things into here, to the w here. We got this guy, and the x becomes this guy. So this one is a w, and this is our x. Because we are doing a feature mapping, so it becomes phi xi, and this one becomes the, by using this formula, is a summation of those guys. And as you can see, they are doing the inner product because we are doing a matrix multiplication. So we are effectively doing the inner product for each of these guys. And because they are inner product, so the WB becomes the summation of all these things. Summation CJ is the parameter you solved in the do problem. You got it. And the YJ is the label in the data set, either 1 or -1. And KXJ XI. So we sum all this up among all the samples in our data set. This one will become the WX. So by doing the computation, doing the prediction, when we get a new sample Z, ideally we want to compute WT VZ minus B. Suppose we have the feature map, but we don't. So instead of compute this equivalently, we can simply compute this guy minus B. And if this one is greater than 0, then we consider it the prediction to be the first class. And if this is less than 0, our prediction is the second class. So that's why we have a sign right here. So either positive or negative. So that's it. We can get rid of the feed and use only the kernel, the K here. So one thing is that instead of working in a infinite dimension, we are working on a finite dimension. Actually, we are working in a infinite dimension, but we only need finite many computations power to do so. That's one good thing. As our experience for the randomized feature, we know that it seems like more feature, the performance is getting better. We haven't get to the limit of to get the best performance by increasing the number of features, number of randomized feature. we stop when we do for linear regression is only because it takes too many time. It takes too much time to run. But we still see an improvement while we are increasing the number of features. We only stop at that number because it takes too much time. So what if we can get in a huge number of features without increasing the computational time? So that is a solution, one of the cool tricks to solve this issue. A lot of things that we observe from the random feature generation is that it seems like more feature, not only more features is good, we don't even need to handpick which feature is good, because even if the random feature, it seems to work pretty well. So that means we probably have a lot of freedom to choose what kernel is, as long as it's kind of reasonable and it can be mapped into an infinite dimensional space. So by our experience on the randomized feature generation, we kind of motivate our work right here, and we kind of believe this should work because of our experience on the randomized feature generation. So one popular kernel is called the RBF kernel. The RBF kernel is considered to be quite easy. We simply consider the distance between these two guys and using a nonlinear way to apply on this distance. If you don't have this guy, it will become the original space. If you don't have this square and you don't have this exponential, in fact, if you only have the inner product between this x and x prime, then it will become the original space. But here, we are using the distance. So distance is different than the inner product, but they are related. And we are actually using the distance, the square of the distance. So it becomes x squared plus x dot x prime plus 2x dot x prime plus x prime square. So it's a little bit different. And we also apply a nonlinear function here, exponential function right here. Another way to feel it is this is sort of like similar to the formula of a normal distribution. So anyway, this is we give it a name, the RBF kernel, the radial basis function kernel. As the name suggests, if two guys, I mean x and x prime, this function only depends on the distance of the radial. Only depends on their radial, because if two samples have the same distance in the original space, then the kernel of these two guys, or the inner product between these two guys in the new feature space, will be the same. It only depends on a single variable, that is the distance between these two guys. So that's called the RBF function. An RBF function is one of the popular, probably the default kernel that you can use in support vector machine. Although there are other kernels, but I think this guy works quite well. And if you are using support vector machine to do the real things, to do the real work, you should use RBF kernel. you can explore other kernels, but as well. But I mean, if you haven't tried the RBF, you should try it. Okay. This is the decision boundary if you are using the RBF kernel. You can see that it is already quite similar to the circles. Uh, this one is already is also in our repo, in the notebook in our repo. Sometimes the decision boundary will not be as close as circle as this guy. The reason that it is very close to a circle is because we have more samples right here. This is a modified example because originally I choose less samples so that it will, let me do it right here. How many samples do we have? We are using RBF here. Our C is like 10. You can change different C. How many samples do I have? Okay, 1,500. Let me choose just 500 samples. Let me restart. Let me just use 500 samples. You can see that if we are using 500 samples, this will not look as like a perfect circle, like what we show on the slide. That is, but you can still see that these boundary are quite are still quite good. Are still quite good right here. We can choose different C to make it more strict because we know that it is very it is in fact circle separable. Let me run on it again. Okay. The thing is that I'm using IPYML. Okay. We probably should use a larger C right here. I'm not sure which C is better. Let me copy this cell to another one because I want to keep this graph right here. Let me put a different C right here. Okay, it doesn't seem to get any better. PLT show. Do I need PLT show? Okay. Let me run it again. Oh, no. I probably should just use the inline here to make it the iteration much more easier. Let me just use the inline here first. The IPYML is only for the 3D things so that I can interact with it. It makes my experiment more difficult here. Okay. I don't remember which one make it more strict, the larger one or the smaller one. Okay, it seems like if you put the C to be larger, it will be more strict. It will be more strict because we already know we don't need soft margin. So if I'm using a larger one, it will become more like a circle. But so if you want the boundary to be like a circle and you know the data to have no noise or very little noise, you can choose a bigger C. Or you can choose to generate more samples. So either way, we will have a better boundary. So because we already know that it should have it doesn't have noise. We don't have any noise right here. We are generating this data using a strict formula to do so. So there's totally no noise right there. We can even use like, so we can make this C to be greater so that it has a hard margin, not a soft margin. Let me run it again. In line here and here. Okay. So if I have less samples, because you have too little samples, it cannot determine the good thing. But you can see that it is hard enough. A lot of factors are in fact on the margin. They are support factors right here and here. You can see that. And it is still perfectly separate these two different classes. But because we are given it too little samples, and we are not giving it quadratic, the polynomial quadratic features, so it cannot find the feature directly. But once you give it enough samples, like what do we do for 600 samples right here? Why not? Because I probably should. I don't know why not. Okay. Still not good enough. Probably should have more samples. Yeah, should like this one. It will become more like a circle. So the thing is, the RBF can work pretty well no matter what feature you have. If you have enough samples, then it will work quite well. As long as you provide enough samples to it, it works quite well. However, one thing that you have to notice is that the computation cost. Because when we compute this guy, we have a summation right here. And it is summation from 1 to n. The n is the number of the samples in your training data. So if your training data has a lot of different samples, like 1 million samples, the computation will cost a lot of time. No matter, not only for the training, but also for the prediction. So even in the prediction time depends on the size of your training data. So that is totally different from your experience with like neural networks. When you're training a neural network, no matter how large your data set is, the prediction time is the same as long as you have the same size of your network. But for a supervised machine, if you are using the kernel trick, the prediction time is correlated, linear correlated, positive linear correlated to the size of your dataset, your training dataset. So that means if you have a large training dataset, it's probably not a good idea to use supervised. If you have a huge dataset, or like you have 10 billion samples or 100 billion samples, then it is probably not a good idea to use supervised machine. Especially if the kernel, the computational kernel takes some time. So it is more suitable for the case like 10,000, I think 10,000 samples. It will work pretty good. Okay, so this is another view, the three-dimensional view. You can see in the notebook. of the how it's separate. Although it is not as perfect as clean as the surface that we see for the polynomial feature, you can still see that how it separate the two different class, the red class and the purple class. This another view is more clearly to see. Again, this example is an analogy to the toy example for the positive and negative numbers. So you can see the positive. If you recall the toy example of positive and negative numbers, the positive samples have a y value 1, and for negative samples, it has a y value -1. So you can see that the red samples are kind of above the z equal to 0 because they have a value 1, and the purple samples are on a plane that is lower than the plane that the red dots are live in. And this is the line separate them. So if we are using the hard margin, the support vector, the surface will pass through these support vectors in the red and the support vectors in the purple. Okay, so that is the explanation of what the support vector machine can do. And we also apply it on the MNIST dataset. There are several different ways of doing multi-class classification, or because it is essential to do that for MNIST. You can see that this is a typical one VR, one first, the rest. So basically, we are still consider the binary classification problem. It's just that we are dealing with 10 binary classification problem. So for each of the binary classification problem, we pick one of the digits against the other 9 digits. So we have 10 different decision problem, binary decision problem. So we use this 10 different binary decision problem, the result of this 10 binary decision problem, to decide which one we should pick, which digit is our prediction. So of course, the one that seems to be more certain or have to have a better, because we are considering the class contains one digit to be the positive class. So we're actually picking the wx minus b to be the most positive one to be our class. So we have 10 wx minus b for each of the binary classification problem. We pick the one that has the largest value. So that's one VSR. In fact, you can design all the different things, because the idea is that we have a tool that we can do the binary classification. We can do a binary classification. We just use the binary classification to arrange or to find out the best one out of these different classes. In this case, because for MNIST we have 10 different classes. And in fact, you have already seen this different method in the real world, in the sports competitions. In the sports competitions, a lot of different sports competitions, you are actually doing the binary decision problem. That is, when two people or two teams play basketball, play tennis, play baseball, or play other like boxing, you're basically doing a binary classification. We're picking a winner. We're picking a winner out of them. So we have a different ways to pick out the champion. you can use all of these different methods that you have seen in the real life to pick the champion, and you simply manage a series of competitions, a series of games. All these games are binary. They have binary result. Either the team A win or team B win, and you use this result in a serious competition and find out who is the champion. So that's a basic idea of applying a fundamentally binary classification binary classification method to apply it on a multi-category classification. That is what you can do. Of course, since like the logistic regression or many different methods, you can find a method or algorithm specific method to modify it to become a multi category classification, like the multinomial method. You can do that. But the idea here is, even though you didn't find a more clever or elegant way to modify the algorithm, you can still use the binary classification tools to find out the best one out of all of the guys. Another analogy is like sorting. But before we go to the sorting, let me use an analogy of the sports game in this OVR. The OVR is like, suppose we have 10 tennis players. We want to decide which one is the best. We are using a very strange way to decide the champion. In each game, 9 of the players are on one team, on one side, against one player on the other side. And they kind of competition to play to each other. Of course, in the real life, if 9 players are on the one side of the court and one player are in the one side of the court, it will become really difficult for one player to get any points. It probably will get just 0. Yeah, perhaps it will get some points at some time, because 9 players have to be cooperate perfectly. But in real world, maybe they are not cooperate that well. So I believe that in some chances, the single player will get some points, but it will be a huge differences between their points. So maybe a more realistic way is that the team of 9 players, they take turns. So they play it one by one against the other one in that game. So it is still a binary. It is still a binary result. Either the team 1 wins or get some points, or either the team 2, team with 9 players win. And we can see a result, how many points they get. Okay, so we have actually 10 games. Each games we pick one player as the player as a team of single player, and the other guys in the other team. And we have 10 different games. And of course, most of the time, the single or every time, we can expect the team with single player lose the game, because the difference is just too large. They cannot overcome the differences between it's just outnumbered, but they still get some points. So if the one performs the best, then we pick him as a champion. So maybe it does not make some sense in some case, but it is a method to do that. So OVR is an analogy to that scenario. Another scenario for using the binary result to a multi-class is sorting. In sorting, like bubble sorting, or in other compare sorting, all of the sorting in the category of comparison sorting. In each time, we only have one operation that we can compare which one, two elements, which one is larger and which one is smaller. That's all we can have. So effectively, this is a binary classification. We have only which one is larger, but we can also use this binary operation to find out which one is the biggest one, and which one is the second biggest one, or which one is the smallest one. So that's the idea. You can use binary classification tools to do a lot of different tasks already. I also mentioned that we use PCA right here before we do the SVC, because SVC can take a lot of time to train. So we use PCA to do the reduction, dimensional reduction, which we will also talk about it a while later, a moment later. But just remark that the reason that we do the PCA is because it can take too much time if we use the original component directly. It can still work. Sometimes it will actually help you to reduce the noise so that the performance is getting better also. But the primary reason that we are using PCA is because if we are using the original 784 features, it will take too much time. If you do what we did right here, it will become, the training is pretty fast and the accuracy is good. We got 98.39 accuracy percent accuracy. In fact, it can achieve more if you do a lot of adjustment and tuning. Like you can tune in the PCA, tune a different C, tune different decision function shapes, doing a lot of different things. You may get a better accuracy, like 99%. But as easy as almost the original phone or typical usage of the SVM, we can get like 98% accuracy. It is much faster than what we do for randomized feature for the linear regression or the logistic regression. There are also like kernel version of like a linear regression things or logistic regression things. You can do things like that. Just saying that there are also something like the kernel version things. SVM can also do regression. There are different ways to do so. One way to do that, a typical way to do that is this guy. We still minimize the norm of W, subject to this guy. Yi minus Wxi minus b less or equal to epsilon. This is one way, one version of SVM regression. So SVM, although we use SVC, that is SVM classifier, a lot most of the time, but it can still do the regression as well. It can do the regression as well. So one of the benefits of using scikit-learn is that, as you can see, you can replace and try a lot of different classifier or regressor without change too much of your code. So you can look through all the different classifiers into the library of scikit-learn into the whole library of scikit-learn and to see which one you need, and just try a lot. There are a lot of different classifier. I will mention a bit some of them. This one is a decision tree. Decision tree, the idea of decision tree is simple. That as we building a flow chart, or kind of like a flow chart. Basically, it's a decision flow chart. So for each of, we start from the root. For example, if we are doing for the iris and decide which class it is, then this is the training result. Of course, the training requires some algorithm, but we are not going to in the detail. And it also, because it is optimization problem, it also requires some optimization goals. And in fact, the problem is so difficult. I think it is at least NP hard. So most of the time we are doing it approximately only. But you don't need to worry about the algorithm to optimize it. Let's just see how it works to do the prediction. So first, we check one of the feature, that is petal length. If it is less or equal to 2.45, then we decide it is the class status. If not, let's check the second condition. What is the petal width of, if it is less or equal to 1.75, then we go to this way. And if it is not, we go to this way. You can see the color of each block to indicate how likely it is to be which class. Okay, so in here, if it is not less or equal to 1.75, then we check the petal length. If it is less or equal to 4.85, then if it is not, then we know it is, our prediction is it is the Virginica. If it is the case, then we go to the second, another round of decision. Okay, by observing this, you can see that one parameter should be how complicated this tree is. This tree, for now, this tree is a binary tree. The decision tree is a binary decision tree. Well, our decision is only yes or no. So one variant might be, okay, maybe we can see like, if we want to check the petal length, maybe we can have several different categories. But in the basic decision tree, we are only deal with the binary decision tree, and it is already quite usable and more typical to see these things. And another thing you can observe is that every feature, in every decision, we are only considering one feature. We're not considering the petal length plus the petal width, or 2 times the petal length plus 3 times the petal width. We never consider this sort of features. So, in the linear regression, logistic regression, or SVM, at least it will do some linear combination to the features. So it will combine the relation. You consider relation between 2 different features. But in this case, the feature selection or feature transformation is sometimes is quite important. So for example, for the thing that the points in a circle, inside a circle or outside a circle things, if you only give the quadratic features like x squared, xy, and y squared, it can still not determine whether this point is inside a circle or not, because we probably need x squared plus y squared. If you give it a feature x squared plus y squared, then it's fine, because it can determine, or if x squared plus y squared is less than 1, then it is in the first class. If not, it is in the second class, things like this one. But if you only give it x squared and give it y squared, it cannot find out how. I mean, it is not enough to find out which point is inside circle and which point is outside circle. At least not in one run. But it can do a lot of different runs to approximate it. In fact, if you give x squared and y squared, it is actually give us less information than give x and y directly, because x squared is in fact removed or discard some information. We don't know whether it is positive or negative. So you might want to keep the original x or original y instead of, discard the information of negative or positive. But in our case, the circle, it will probably give you some benefit because they are symmetric. But in general, x squared, the feature x squared, does not give you more information or any advantage, discriminative advantage than the original x. But in the case of linear SVM or linear regression or logistic regression, given a feature x squared can give you a lot of different, can change things a lot. Okay, let's see a decision boundary. The decision boundary of logistic regression, linear SVM, the linear regressions are all straight lines. Although I mentioned linear regression a lot, please recall that linear regression is not suitable for classification. It's just like what we discussed in last week. We can do that, but we don't have to do that. So mostly I'm just saying logistic regression and the SVM. We can see that the decision boundary is straight line and can be a curve if we are applying a feature engineering. But for the decision tree, for the reason that we just mentioned, that it only use one feature at a time. So you can see that each decision boundary is either straight or vertical. It is straight lines, vertical or horizontal. And how many turns of these things depends on how the depth of your tree. If you have more depth, then you will have more turns like this one. If you only have one depth, you probably have just a straight line, and it is not any straight line. It is either vertical or horizontal. As you can see, that if you have if the tree to have a very deep, have a deep depth, have a large depth, then we can in fact to do the boundary to be very close to our samples and can separate them perfectly and perhaps too perfect. So one of the key hyperparameter or restriction is the depth. If you have a infinite depth, then you have a lot of risk to overfitting the data, because as you can see, we can simply draw an arbitrary shape along with these samples, and perhaps you can even do things like this one. Let me draw it like this here. You can even do things like this one. Like a square here, square here. Right? If you have enough depth, you can actually draw a small bounding box around each of sample. This is definitely overfitting. This is definitely overfitting. For a case of logistic regression or SVM, even if you have a higher dimension feature, it still have certain restriction. It will be not as worse as this guy, because in this case, you have a simple solution to find a perfect. If you don't have any restriction, you will. It is too easy to find a perfect fit for your data. Okay, I'm losing my. Okay. Cursor. I cannot see my cursor. Okay, I don't know why, but I cannot see my cursor. Okay, let me just use my hand to do this thing, this touch screen. Okay, don't worry about it. But the benefit of decision tree is that it is very explainable. One thing that people kind of hate or talk about the neural network is that it is considered to be something like a black box and non-explainable. But the decision, on the other hand, the decision tree is totally explainable. It's totally explainable. You can see every decision, how it makes a decision. Personally, I think the explainability is a little bit overrated, because at least in some case, because the explainability or interpretability here is, in some cases, it's only we want to satisfy our need to understand things so that we can make sure it doing it correctly. But the thing is, the problem we ask the machine learning to do, we want machine learning to do, is usually too difficult to explain it as clearly as this guy. So it is probably the problem itself is very difficult. So for example, let me give an analogy. Like the Fermat last theorem. We know that Fermat last theorem is solved in the 1990s. But for general public, the proof is too difficult to understand. For you guys, or even for me, they looks like a black box. They looks like a black box. If you want to find some proof of the Fermat last theorem that you can easily understand, and every step you can clearly to realize how it works, it's probably a wrong proof. A lot of guys try to find a proof of Fermat last theorem or other famous mathematical problem that we call the Minke, or in English, I think it's correct not scientist. I used to receive some emails about people pointing out Einstein is wrong. The light is not a constant. It's something like because the friction in the air to give it the illusion that light has a limit there, but instead the light has infinite speed. It gives a lot of things like that. Since similar in mathematics, a lot of people give some proofs of Fermat last theorem or other famous mathematical. They use fundamental method that you can sort of understand each of step, but they are wrong because the problem itself is too difficult. It does not have a simple explanation. If you want to prove it correctly, it will become something very, very complicated. It is essentially the black box for like general public, or maybe like most of people in the earth, on the earth, except like maybe just 100, 200 people, they might understand the proof clearly from the beginning to the end. But for the rest of people, I mean the whole population minus, let's say just 1,000 people, a whole population minus 1,000 people, probably people don't fully understand every step, cannot fully comprehend the whole proof of formula theory. So it is if essentially like a black box to you. And probably if a problem is so difficult, it should be a black box. So if I have to choose between the overfitting or the black boxness, I will choose black boxness instead of overfitting. So instead of the explainability or things like that, I will if I can, I mean, if I can both have all of the good properties, then that's definitely I would like to have all of the good property, including the explainability. But if we have to choose, and probably because the nature of this problem, it is too difficult. If we have to choose, we have to choose the correctness instead of the explainability. And we have, I mean, after all, the reason you want the explainability, part of the reason you want the explainability is you want to ensure the correctness or robust of this the trend measure. If you don't understand, I mean psychologically, it is difficult to trust something you don't understand. But we have other way to do that. We have other method to check the reliability or robust of the model. So instead of focusing on the explainability, probably the other method should be considered to ensure the security or the robustity or the safety of the models. Okay, so that's just one thing that we talk about, because decision tree is probably on the opposite spectrum to the neural networks in many sense. Okay, so there are other, but I'm not against decision tree. It's just if you are trying to use decision tree, it is suitable for certain type of problems. And one thing you have to remember is you don't want to, you have to have other assistant a restriction on this decision tree, because in the nature, if it doesn't have any restriction, it is too easy to have a small bounding box around each samples. So you probably want something like limited the depth of the tree. That is probably the first thing you want to do. You probably want it at the beginning. You want it to have only 2 depths to as a baseline, and increasing it one by one slowly. And another thing is that you can combine with other methods, ensemble methods like a random forest or actual trees, or maybe with ADA boost. ADA boost is another boosting method that can making small weak classifier into a strong one. So you can combine decision tree method with other method like random forest, actual trees, and ADA boost. There are more advanced methods like a gradient boosting method, like light GBM, or the gradient boost classifier inside the scikit-learn. It also provides a histogram-based gradient boosting, like light GBM, inside the scikit-learn. You can also use this method with certain suitable parameters. It can work very, very good. And sometimes if you are working with the tabular data, it might be easier to achieve good performance than using neural network in a lot of time. I mean, at least in 2000, in the year around 2015, methods like this one, like XGBoost, cat boost, or like light GBM, or even random forest. I like random forest. It is simple and it is a very simple and a good baseline. This method works very well in a lot of Kaggle context computations and can beat a lot of neural network based method. So they are very useful. Even today, they are very useful. So one, you can try it like random forest or the gradient boosting method in scikit-learn, as well as using light GBM or XGBoost or like cat boost. These are probably three most famous boosting tree boosting method libraries that you can find. XGBoost is probably the oldest, or at least become famous first one, and later it comes to the live GBM and cat boost. Light GBM is currently is developed by Microsoft. And the cat boost is developed by Yandex, Yandex, which is you can consider is a Google of Russia. Yandex also has a database system called the ClickHouse, which is also a very good and fast database system. And I think it combined with the capability of CatBoost with the ClickHouse together, so that you can easily apply the CatBoost on the ClickHouse database system. Because Light GBM is, a lot of people use Light GBM and it is quite easy to use. I believe it will combine with work very well with other Microsoft product. XGBoost and the CatBoost also, all of them provide some compatibility with scikit-learn. So at least you can use the dot fit and dot predict this paragon. They have some API follow this paragon. Okay, in scikit-learn, it also has neural network, which is called the multi-layer perception. Sometimes you call it the feed-forward network, but the most accurate name should be multi-layer perception. Multi-layer perception. So you first define the MLP classifier, and one of the benefit of using this, you can define different solver instead of using a gradient descent based. LBFGS is, I think, is semi-quadratic optimization. In contrast to the linear method like gradient descent or gradient based method, it is semi-quadratic optimization method. Although there are better optimization method, more advanced optimization method. People are using gradient based method on neural network for reasons, because certain properties of neural networks, so that the advanced optimization method may not work that well. But because LBFGS is very popular, and chances are it will work better in your case. So you can still try it. So this is an example. Because it only define the simple multi-layer perception. So all you need to do is provide the size of hidden layers and maybe the activation, the nonlinear functions. You can specify the nonlinear function. So in some case, if you are just trying the simple neural network on a simple dataset, on TOEIC dataset, and you are very familiar with scikit-learn, you can use this as well. But personally, I don't think I will use this very often, except for teaching. Otherwise, I never use this guy. Um, I never use this guy in any experiments or serious works. But there it is. You can use it as well. And maybe sometimes, I mean, it is still functioning perfectly. So you can, uh, I can still imagine that in some situation, you will use it instead of using PyTorch. Uh, but also note that we will going to introduce a library that is compatible with scikit-learn, and it has a backend, a PyTorch backend. So maybe if you are really try to use neural networks on scikit-learn, maybe you have a pipeline already built with scikit-learn, and you want to change from like a gradient boost to neural network, then you can try the library I will going to introduce later. Okay, so after the those classifier things, let me go through other functionalities that I think is very useful when you want to use when you use scikit-learn, and they are, although they are not as fancy as neural networks or as iconic as classifier or like regressor. These are very useful tools. Time to time, you will going to need or at least take some idea of them. So first of all is the Gaussian process. Gaussian process. What is Gaussian process? You can think it is doing interpolation, like a polynomial interpolation or other interpolation of these samples. For example, we have this observation that is a sample, the training data, like this one, this one, this one, this one, and this one, and this one. It's kind of like linear regression, but we are expecting to find a curve that fit exactly. The difference is that not only we are trying to find the curve itself, our prediction is this red line. We are also trying to estimate the errors. So we know that, okay, this is observation. So we are 100% sure this curve will pass here, pass this point. And we are 100% sure that the curve should pass here. So we have a perfect prediction on here. But on the other prediction, on the other points, we are not, we don't have 100% certainty. So not only we give we give one prediction, we give a range of prediction. We give a prediction as a distribution, as a random distribution. So we are not given one prediction. We give a probabilistic prediction. We are predicting, okay, this should be lying. We are giving a prediction that is a probability distribution. That is a probability distribution. So this prediction is a normal distribution. In general, it is a normal distribution. That's why the Gaussian here. Not exactly quite a Gaussian here, but you can imagine because we are involving a lot of Gaussian distribution. So the prediction is probably on each x is a Gaussian distribution. The mean of this Gaussian distribution is indicated by the red curve. And we have some 95 confidence interval indicated by this orange band. So this is a Gaussian process. So time to time, you probably will face the request or asking for, okay, how certain is your prediction? So Gaussian process is one of the major method or one of the solution that can either you can use it directly or give you some modifications, motivates you inspirations to modify your algorithm. So sometimes even if our observation is have noise, sort of like the case for linear regressions. So in this case, the observation does not guarantee the 100% certainties. So there's a variation on Gaussian process, Gaussian regressions on noise data set. So you can see that the band, we still have a band on the observations. It just narrowed down, but not going to be zero. The height is not going to be zero. Basically, the Gaussian process is just it's actually quite intuitive and naive to combine several Gaussian process together. I mean Gaussian distribution together to do some interpolations. So you can definitely check the mathematical formulas behind it. Sometimes you may, I think a lot of you may wonder, have some fundamental idea, or always wonder, okay, we see all these advanced techniques like the deep learning things, deep neural networks, or a lot of different techniques. Can we just simply use some simple method to do all these machine learning things, like what we will say density estimations, or we can do something like a nearest neighbor, but just doing it softly. In fact, Gaussian process is kind of like this guy. We just combine all these samples, make it soft, and combine them together. So one way to see that is the Gaussian process classification. Now here we have a XOR dataset. That is, one dataset is on the like the first quadratic and first quarter and the third, and the other is on the second and the fourth. So this is called the XOR problem. So we get a lot of different samples, like the blue one and the orange one, or the blue one and the orange one. So how do we find the decision boundary or the confidence? Simple. For each of the sample, we can find a Gaussian distribution around it, and we sum them together. Or kind of like the mixed Gaussian mixture model we would introduce a little bit later. And we use the result to determine our boundary, because we already have a so say that for each the orange one, we draw a negative Gaussian distribution around here, Gaussian function around here, and for the purple one, we draw some purple, I mean positive things around it. So we can still construct a function, right? And after we construct this function, we sum up all of them together. So if something, the function value is positive, then we decide it to be the blue purple one. And if the function value, the final function value is negative, we are classify it as a red or orange one. So that is Gaussian process. So it's very intuitive, and probably if you are thinking about similar things, it's probably one of the things to realize one of the fundamental, the most obvious or naive ideas, and it actually works quite well. This is the doing the things on the iris dataset. We are doing RBF. I mean Gaussian processes is kind of like RBF, doing these things on the iris dataset. So kind of like putting a lamp on each of the sample and to see what happens. If you're putting a red lamp on each of the red sample, a green lamp on each of the green sample, and a blue lamp on each of each of blue samples. So at the each point in this space will affect by all of the light emitted through all the samples. But of course, if it is more close to the red samples, it will become redder, more red. If it is close to some more green samples, it will become more green, and so on. So it will become a very natural way to do the classification. Another related concept is the Gaussian mixture models. We are trying to fit things. Usually, we are trying to fit things in Gaussian models. Like if we got a grade of, all the scores or grade from a test for each person, we probably model it as a Gaussian mixture, or we get the salary of like the statistic of each. Do a survey to get the salary of each people in Taiwan. Then we probably will model it, fit it into some like Gaussian distribution or other distributions. But sometimes it is clearly not a Gaussian distribution. It has two mode. It will have clearly two mode. Then we are going to fit it with a Gaussian mixture model. That is kind of like the mixture or the summation or weighted average of two Gaussian distributions. There are methods to do so. No matter how many Gaussian distribution inside these Gaussian mixture models, like 2, 3, 4. There's method like called the expectation maximization algorithm to help you to find the fit. It's more difficult than to fitting with just one simple Gaussian distribution, because if you want to fit the Gaussian distribution for the data, you only need to find out the there are different goals, different loss functions. But one way to do that is just to find the mean and the standard deviation, and you get your Gaussian your Gaussian model, Gaussian distribution model. But for Gaussian mixture models, it is much more difficult because the mean doesn't mean much sense. So you need some algorithm to do so. But there are algorithms readily provided, so you can use these things to do that. So here is some examples for a 2D Gaussian mixture. Because Gaussian mixture is usually can be visualized as a circle or elliptic. So here gives some different variations. Like we can assume each of the Gaussian is spherical. That is, the x and y are independent and have same standard deviation. Or we can assume them to be sort of x, y are independent, but they can allow to have different standard deviations. Or maybe they can have correlations and different standard deviations, all of these things. But each of the Gaussian mixture, each of the Gaussian distribution has the same covariance. Or you can have the full freedom. Each of the Gaussian distribution inside this Gaussian mixture has its own, covariance matrix. So there are different assumptions you can use. A lot of time, so if you see that the distribution have two modes or many different modes, and likely to have different modes, then you probably should use Gaussian mixture models to fit it. Another task that people do a lot is clustering. Doing clustering. clustering, the difference between clustering and the classification is that we don't have label. So clustering is usually considered as unsupervised learning. So for example, suppose we have two circles, a smaller one and the bigger one. How do we separate them in different classes? So the most intuitive and the straightforward is that, well, okay, we have two different classes. One is the larger circle and the other is inside inner circle. So you can see that the DB scan, HDB scan, and the optics, all these three are similar method. They doing a very good job. And you can use Gaussian mixture to do that, but it doesn't work very well because if this is too Gaussian, because they are not Gaussian, so it doesn't work very well. Gaussian works well for Gaussian mixture works well for this sort of things, like this one. Of course, in the second row, we probably want to it have two different class, the upper curve and the later curve, the U curve and the upside down invert U curve. So some of the algorithms doing it quite well, like DB scan and HDB scan, optics, all these three doing quite well. The Gaussian mixture got lucky a little bit, but doesn't work that good. Okay, also the spectral clustering seems to work just as well as a DB scan method. But for other tasks like this one, just like these three different clouds, it doesn't work that well for DB scan or HDB scan. But it seems work quite well for the Gaussian mixture and k-mean. This is the mini batch k-mean, but okay, this is a variant of the k-mean method. And still the mean shift doing well, and also the spectral clustering. So you can see that all these common use method. I will introduce the k-mean right here, but you can see that k-mean is k-mean is the most common use or most referred the clustering method refers to. But there are other things like DB scan is also very popular, and the spectral clustering. By using k-means, you need to have to decide the k at first. How many means do you need? But scikit-learn actually support many of other methods that it can decide the k for you automatically. Like DB scan can do that, but that is probably why it doesn't work that well in this case. But after all, there's no correct answer because this is unsupervised learning. So maybe this one is, if you can change some parameters, maybe it can work better. Okay, then there also something like Gaussian mixture and DB scan, HDB scan, and optics. These three are similar to each other, and you don't need to decide the k at the beginning. You need to decide the sample, how many samples, and epsilon for DB scan. So, but we describe a little bit about what the simple method like k-mean is. The k-mean is quite simple. At the beginning, we assign a k here, like 1, 2, 3, 4, 5. For 1, then it is just kind of like we just find because it only have one class, so we are trying to find the average point, the mean point. But for each, if we came in, we are trying to find k different centers, and for each samples, we are categorize it to be the nearest center, and will compute the distance between each sample and its corresponding center, its nearest center. And we try to move around to adjust this center. So the distance between samples and the centers can be minimized. So that's the idea of k-means. So it is an optimization problem. It requires some algorithm, but if you are familiar with gradient descent, you can also do it with gradient descent. Of course, you can do that, or doing some approximate method to do so. But this is basically what k-means do. However, although it seems to be quite reasonable and nothing can go wrong, except of course you find the wrong case. But there are actually more things need to be considered for doing cluster. So although k-means is very popular and frequently used, it still have some pitfalls. We are pointing out here and to help us understand more about what the issues we need to consider for doing clustering. One thing is that if we give it a wrong k, for example, it should have 3 different classes, 3 different clusters. But if we assign the 2 inside it will definitely do things like this one and does not doing very well. So of course, one way to solve it is we can try different cases and to see which one is the best. And of course, we have to come up with some formula or method to decide which one is best. That's one method to do that. But there are more issues than just simply to decide k. The other issue is that sometimes the nearest we want to cluster things, but the cluster does not need to be the samples does not being in the same cluster does not equivalent of saying they are all have small distance. For example, in this case, clearly we intuitively think this guy is a cluster, and this guy is a cluster, and this guy is a cluster. So although this point and this point should be in the same cluster, but their distance is much larger than the distance between this guy and this guy. So the distance is not the only criteria for determining which points should belong to the same cluster. So we probably are thinking something like the locally dense or locally consider the distance in locally but not in globally. A lot of methods are using this idea and develop some different algorithm. And the other thing is unequal variance. So in this example, we should have 3 clusters. This guy and the big one and the small one. So you can see that a lot of the points, the sample that should be in the yellow one is categorized as in this purple one. This is because the yellow cluster is too huge, so that a lot of the distance between the center and some samples in the yellow should be large. But although they are large, we can still, if you see it, we still know it should belong to the yellow cluster. So if you use the distance alone, it does not categorize our intuitions of what the cluster is. Another thing is that even though they have roughly the same size, roughly the same same radius, and they have quite distant to each other. And in this case, the distance is in fact a good measurement. However, if one cluster has too many samples, our optimization goal will more towards to satisfy the needs in this cluster. So instead of given the center evenly in these three different clusters, by given the this cluster two centers, this cluster two centers, the loss will become less, because it can sacrifice these guys because they are too little, they are too few numbers. So it just simply sacrifice the loss of this guy and try to give more centers inside this single cluster to achieve lower loss. So there, although this one seems to be quite straightforward and nothing can go wrong, if you're doing it exactly, you will see a lot of issues in a lot of different situations. So that's why a lot of different algorithm has been developed. But aside from that, let's first go to some applications of what clustering can do. This one is using k-means, but in principle, you can do it for a lot of different clustering methods to do this thing. This one is to do the factor quantization. In fact, the factor quantization method in deep learning, like the Week8 or like Week8, it used similar method to do that. Use k-mean to do that. So the factor quantization method is that suppose we have a limited number in our plate. Like if you have a monitor that can only display like 16 colors at one time. Although it can be difficult to imagine because we are so used to the monitor with full color, and we have powerful GPU and graphic cards. But back to like 30 years ago, a lot of like Nintendo machines or Sega consoles, like in 8-bit or 16-bit era, it is difficult to display full color at once. So there is a limit of how many number of colors can be displayed at once on a screen. Even within today, if you have a e-paper, e-ink reader, e-paper, e-book reader, or maybe you have a LED display, but you are working on a very limited like Arduino or like a ESP32 card to drive this display. You have very limited RAM. Or maybe you just want to print things on a paper. So there are still some situations that you have limited number of color. Or maybe you want to do a digital painting, like you print out a paper and write some numbers in each area, and people see, number one, I painted this area in red, and the number two, I painted this area in green, things like that. In these situations, you might have a very limited number that you can use. So how do we choose this limited number to represent this image? So one way to do that is using k-means. So we are working on a three-dimensional space, RGB space, and a lot of samples. Then we use k-means to choose 64 colors. That is, we actually use 64 means. to clustering all these numbers into 64 different groups. This works well for the k-means because we actually want each color is close to its center, or it's very close to center. We don't need to worry too much about, this color thing. Even though if it looks like this one, we probably still want this clustering because they are still very close to each other. So although we are not doing exactly what we mean by clustering, at least not in the case that we are imagining in these examples, k-mean works well for this case to do a quantized images. So it has 64 colors and it can quietly, fairly close to the original one. Also, there are other methods like dbScan that allows you to use different parameters instead of specify the k. So it will find out the cluster for this sample. It primarily determined by the density. If they are close to each other and the density is large, they put them inside the same cluster. So same things like this one. And it doesn't have to have the spherical shape of the cluster like what the k-means. The k-means always have the spherical because it uses distance. The distance is a spherical thing. Okay, so that is about the clustering. There are also other methods, like one of things is PCA. It is related to the dimensional reduction and the meaningful learning things. So what is PCA? Principal component analysis. Basically, the intuitive is we are trying to find the major axis of the data. So in this case, most of them are lying diagonally in this way. So this one is the first principal component. Because we're going to do a mathematical formula a bit later, but you can see that if we want to characterize one features, just simple one features, just one simple feature that is the major one, the most different one, we pick this one because they are more different to each other. There's a real world analogy that, okay, suppose there's you find out the two people. You don't know their name. You want to refer to one of each of them. You probably will pick out the differences, the most differences between these two people. Like if one has a long hair, the other one is a short hair. You'll notice the length of hair because that is the difference between them. They probably have the same gender, same race, and probably dress similar clothes. The major difference between them is their length of hair. So probably will refer, okay, the first one is a long hair man and the second one is the short hair man. This is simple. We first, the principal component is the things that they are mostly different. So in this case, the most different axis for them is this one. This one is the second. It only have two dimensional. So the important one is this one, and the second most or the least important one is this one. So we can do that in general in higher dimension. To formalize the intuition, first you have to notice that everything is already centered normalized, say centered to be unbiased. Everything has to be unbiased. So the mean is 0. So we already know the center of the data is the origin. That is, we already know that. So in order to see which dimension is the most variant, most has the most difference, we simply pick every x and we run through all the direction. The w equals 1 to means it is a unit vector. So we are choosing the max direction. We just scan through all the directions. We scan through all the directions. For each directions, we are mapping all the data on these directions. And we can see that, okay, how many things are left on this direction. So it is look like a inner product, like an inner product. So for example, on this direction, if we project every sample on this axis, most of the lengths are going to be kept because I mean, for this guy, it will become from this one to this one. It will become shorter, certainly, but not as bad as if we project to this axis, because it will be a lot of length is going to be discarded if we project to this axis. So we're just picking one direction, so that if we project everything on these things, we can still keep the most length after we do the projection. So that is the first, you see the one here, that is the first principal component. So after we get this component, we remove this dimension out of everything. So we still keep the orthogonal space to this dimension. Then we remove this dimension, and then we do this again to find the second most important component, the second principal component, and so on. So one by one, each of the principal component is going to be orthogonal to each other. And the first one is the most important one. And the second one is the second important one, and so on. So it kind of like if you put in some oils, waters, salt together. Suppose we put some salt, some oil, and water, mix them together. It is definitely a salty oil water. Maybe you also put some sugar in here. But what is a principal component? If we are measuring how important by the weight, we simply compute the water should be the most important one because it weighs most. Suppose the oil, we don't have that much oil or that much salt inside it. So we are picking the most important component out there because it contains more weight. You don't remove water. If you remove the water, the weight will reduce a lot. So that is not what we want. So if you want to keep just a single one thing, you probably want to keep the one component that contains the most weight. So that is exactly the same. It's only that we can run through all the directions to pick the one direction that contains the most weight on it. So in fact, if we were writing it down, it will look like this one. And we can use the single variable decomposition to find out the W. So the algorithm is exactly the single variable SVD, single variable decomposition. On a metric, we can do the single variable decomposition uniquely, and we can find a W right here. This W is the W right here. We want. It's the W what we want. So the original feature is X, and we can do a linear mapping by using this W to get the T. And It is ordered by the importance, of each component. So if we want to do a dimensionality reduction, we discard the least important things. We only keep the most important components. So we can pick a number, L. L is the limit. If L is 1, then we only keep only the first principal component. And if L is 2, we only pick the second. And we can reduce original feature like if MNIST is 784, if we pick like 60, like what we did for the SVM, then we can reduce the dimension from 784 to the dimensional 60 dimensional. And this is best we can do if we only consider the linear mapping. And we will keep and remain most of the weight, most of the material inside our data set as much as possible. So this is a PCA for iris dataset. Although we don't do much, because original we have four features, now we have 2. So we didn't do much, but you can still see things like this one. However, PCA does not consider the label. It only considers the data. So it doesn't consider, this one is the Setosa. This one is a versicolor, and this one is Virginica. It doesn't consider any of the different class of each data. It only considers the feature. So we have a lot of 150 different samples. Each samples have 4 features, and we reduce it into 2 by using PCA. So although it still looks pretty good that they separate, seems we choose good features. But if we consider the class, because we have 3 different classes, if we take the different differences between the class into consideration, so that we pick the axis to separate each of the class, to kind of emphasis on we are picking the axis in a different in a different goal. So we are going to pick the axis that emphasizes the differences between these 3 classes. Because we have 3 classes, we can pick 2 dimensions to emphasize this. If we have only 2 classes, we can only pick 1 dimension, 1 axis. Because we have 3 different classes, we can pick 2 dimensions or 2 axes. So this is called the LDA, linear discriminate analysis, kind of like PCA, but similar to this PCA, but it takes the differences between classes into consideration. If we do so, this is the difference. Is the result. Another thing similar is called the independent component analysis. There are different algorithms for the ICA. The fundamental idea is to separate the signal into different subsignals so that these signals are independent to each other. One example is that when a mother is pregnant and have a baby inside, if you measure the heartbeat, you probably get something mixed up with the baby's heartbeat and the mother's heartbeat. But ideally, the baby's heartbeat and the mother's heartbeat are independent to each other. So if we can separate this signal into 2 signals, and these 2 signals are independent to each other, then we can separate the baby's heartbeat and the infant heartbeat and the mother's heartbeat. Similar things like maybe we have people singing, and another people is playing a different musical instrument. Each of them may be considered as the independent signals. If so, then we can separate them together. But probably the most suitable case is a noise and a signal, because for the musical case, each of the musical instrument kind of align to each other. They work to each other. They are not. They are playing the same song, so they are not exactly independent. But suppose we have two different noise. You are playing some violins, for example, and there are some people making some different noise. Maybe they are just trying to fix the toilet or something. There, some noise right there. So we have two independent signal. So by using the ICA, we can separate them together because we can assume they are totally independent. Another category of machine learning is called the manifold learning. So this is a three-dimensional surface, a manifold. The manifold learning is try to reconstruct the metric, geometric of this surface. So although it looks like a S-shaped surface, it is in fact more like, if you flatten it, it should be like a two-dimensional thing, like the rectangle. So can we use this data to find out the structure of the manifold? That is the question. So a lot of time we assume our data is resident inside the high-dimensional space and sparsely in a way that they form a manifold. This is an assumption. So there are many methods to do that. Here is some of the things. One is the isomap embedding. It consider the make it to preserve the distance between every guy and the nearest neighbors. So this is isomap embedding. So this one works quite well for this example. If you are using other methods like a multi-dimensional scaling, MDS, which is in general very useful, but in this case it does not become a rectangle, but it works quite well in some cases. And there are also spectral embedding and the TSNE. So in this case, it seems like isomap embedding works more close to our expectations. But in fact, TSNE and the spectral embedding and even MDS, they are applicable to many different situations. They work very well. TSNE is especially works pretty well for like visualization, since in classification. So for example, let's consider this 64-dimensional digits dataset, kind of like a MNIST, but in lower resolution, or even lower than the resolution of MNIST, and it has only 64 samples. So how do we visualize them so that each sample represents a point in a two-dimensional plane? So one way is to do the SVD things. It can do like a PCA. It is a PCA. We can do a PCA dimensional reduction. It works similarly. And we can do LDA if it considers the difference between class. So it separates the classes even more. But in SVD, I mean in PCA, it is still kind of making the similar digits close to each other. And by using isomap embedding, you can get this one. Still pretty good. And TSNE especially, you can see the most difference and the application of TSNE is it emphasizes on separate the items in different class. So it makes a very good visualization because each class is separate almost discretely or completely. Also, that is how TSNE do, mostly for the visualization. And you can also do MDS embedding. to kind of estimate the manifold of the things. Although it doesn't work that well on S-shaped manifold, but in some case it works. At least in this case, I think it has done a very good job. It doesn't emphasize the differences too dramatically like a TSNE, but still you can see the clear boundary, and each of them are quite concentrated to each other. There is also like a local something embedding. I forget how to do that, but this consider local distance of things. Another thing that we should do is to estimate the density function, the probability density from the samples. For example, we have these samples right here, and we can draw the density estimation right here. There are different sample kernels that we use, like Gaussian, Taphead, or different things. But we can construct, instead of constructing a histogram, we can construct a continuous distribution. And the Gaussian is a common choice and which works nicely. And you can see that it is more smooth and very close to the original. Original is the graduate things. It's very close to each other, to the ground truth. And we have already shown how to use KDE in our previous example, like in Matplotlib. We show some visualization of data. So it is very common used. So you may want to say that, okay, one thing that we do for generative AI is we generate to estimate the distribution and use the distribution to generate things. So if you say that KDE is so good, can it replace generative models, or can at least it can be considered as a generative model? The thing is, it can. In principle, it can do that. So for example, if we are using for the digit example, this is what it can generate. But don't be too excited too early, because this one works quite well. But if you are trying to do things like what we do for generative AI, it probably won't do that good. The reason it doing quite well in this example is because the resolution is quite low here, and we have very nice data set. So each of the sample are actually quite close to each other. It is still sparse, but not that sparse compared to what we usually deal with deep learning. So each of the sample is in fact a combination, a weighted combination of these samples. But since like these two, all of these two are quite similar to each other, or at least similar enough, so we can, so it doesn't look so odd. So one reason is because it's a low resolution, it cannot go wrong. It is already look very ugly, so it cannot. There's nothing can go wrong too much. The other thing is we still have quite similar examples. So if they are mixed together, it won't be look so odd. So that's why it works. But KDE is very common use, but the use case is different than the generative AI things. Okay, the scikit also contains some functionality for doing novelty outlier detection. I won't go to details, and it also has some functionality to do the model persistence, which means you can save and load models. Personally, I like the job lib here. Job lib is a library that used for various kind of niche tasks. I use the dump and load to do the serialization, not only for the scikit-learn models, but also for several other things. And I found out this is kind of reliable for me. So I sometimes I use Pico also, but for a lot of cases I use JavaLib to do the serialization. If when it works well. And also I use the parallel, the JavaLib parallel. I didn't use the memory, the hash, and the register compressor. The memory is kind of like the function memorize a cache of the function result. It seems reasonable, but I don't have any chance to use it. But I use parallel. Among with other solutions, I think I found that the JavaLib's parallel kind of robust and useful for many and lightweight in many cases. So that's why I use them. Okay. Okay. So I don't go detail, but the JavaLib parallel is quite useful. Probably I put it right here. It should be in the next slide here. So you simply write a function and use parallel njob is equal to 2, and it will do the parallel things in Python. So Python is notably difficult to do things in multi-thread. So you have to do multiprocessing. And the multiprocessing can give you a headache when you want to pass through data. But since JavaLib including the serialization seems quite well, so I found the parallel of JavaLib is very useful in some cases, and it is very lightweight, very easy to use. You don't need a server or even running you can even run it in a notebook, and it works well. Here is a guide of how to choose which model, like classification, clustering, regression. You can find the slides and click this just like I did to find the original one here. If you are not familiar with things, you can follow it. It's quite fun. For example, for the first step, if it asks whether you have more than 50 samples. If not, get more data. Don't do it. If yes, then does it your job involving with predicting a category or not? If yes, you go here to see if it is classification or if it is clustering. If not, it's probably a regression or maybe like a dimensional reduction. And when you go into the classification, you can simply follow this guide to choose the classifier that is most suitable in your case heuristically. Okay. We're probably almost done with it. So lastly, let me introduce other libraries in the scikit-learn ecosystem. So they have similar API as scikit-learn, or they can work with scikit-learn. So first of all is a Dart. Dart is a library for time series machine learning tasks. It contains a lot of different algorithms. As you can see that it can construct, it works very well with the pandas. It can construct time series from data frame or from NumPy array. So it has a time series data object. And when you want to do the training, you can simply use a scikit-learn-like interface to do the fit and to do the predict. Here's one example that the prediction of the time series and the ground truth. It contains a lot of different algorithms, including some things like XGBoost, LightGBM boost, cat-boost model and neural network deep learning model like in PyTorch, like RN models or like NBITS models. This is just part of the whole list of the algorithm available. Because it's just too long, I can just pick a slice of them. Another library is Scorch. Scorch is scikit-learn meets PyTorch, as its name suggests. So it gives the PyTorch a scikit-learn interface, so it can make PyTorch work with scikit-learn. So for example, you define a model using PyTorch. This is just PyTorch models. And you are using wrap these models inside a neural net classifier. It also has a regressor as well. And it will works like a scikit-learn classifier. So it can fit or predict probability or predict all of these things. Personally, I use Lightning as a convenient wrapper for the PyTorch, but this one also works. I use it in one of the projects, but because I prototype using the scikit-learn, and so it is a reasonable choice, rational choice for keep all the code and just replace the model to be a PyTorch model. But I found it not that easy. It doesn't worth it. For me, I think it doesn't worth it because the flexibility and a lot of different compatibility. It will have some compatibility issues. But it is a choice. It is a tool that you can consider about. One benefit of Scorch is that it can integrate with the scikit-learn pipeline. Just as a remark, the scikit-learn has a pipeline things. You combine different things into one pipeline. And also you can use the grid search functionality in scikit-learn on the PyTorch model, which is interesting. But I still don't think. Maybe if you want to use this functionality, you can consider about it. But I won't use it to train the model because it has too many limitations. But if you are trying to do something like integrate into a pipeline, or maybe you just do a one-shot research, then you can use it. Also, XGBoost has a similar interface that you can use maybe easily with scikit-learn, and KBoost also has an interface. They're not that compatible, but at least it has a fit and predict problem. So you can work with some of the scikit-learn models, scikit-learn code. Other things like in a package called imbalanced learn, which works well with scikit-learn and dealing things with imbalanced data. And Desk is, which we probably mentioned it before. It can do a lot of things, mostly because it can consider as a pandas alternative, since can deal with the big data, can do the parallel process, distributed computing. So it also has machine learning capabilities similar to the scikit-learn interface. So you can consider it as a replacement. I'm not sure it is a drop-in replacement, but it is a viable replacement if you are consider more distributed, more multi-process, distributed learning things for large data. Another thing I want to mention is the states model. States model is a Python module for doing statistics. Although SciPy has some states functionalities, comparing to R, it lacks a lot of functionalities. So states model is the go-to module, if you require some statistics functionality in Python, that does not exist in other place. So it mostly doing it while using it for statistics. We're mostly using it for statistics, not for machine learning, but because like the linear least square, ordinary least square, or other things are kind of like the statistical machine learning functionalities. It provides some user interface, API interface, similar to scikit-learn. So this is how it works, kind of like a scikit-learn, and it achieves like 99% accuracy if you're using a teapot here. And finally, beside the scikit-learn, there are some alternative machine learning library in Python ecosystem. So scikit-learn is not the only one. One that people use and the require mention is the PyCorrect. I think the root is also coming from R. But it focuses on local machine learning. It is also very comprehensive. Another is the Orange. Orange is another machine learning and visualization framework. It is mostly for the. It has a very great user interface, and you can try it without writing too much code, or maybe even doesn't use any code. You just select the method you want to use, the algorithm you want to use, and choose the parameters. Okay, so that's all for today's lecture. Next week, we're going to talk about PyTorch and other deep learning frameworks.